Well, good afternoon, everybody. Hope you're doing well and those around you are doing well. I will maybe just wait another minute or so to get everybody online. Okay, so I looked at your syllabus and I was reminded that your next midterm is going to be Wednesday, April the 8th. And so that means that today's lecture will be the cutoff for new material for your exam. Okay, so whatever we get through today, that's where it will stop. Okay, and then the plan is sometime this weekend, maybe even before, like maybe Friday or something. I will post your practice midterm homework assignment, and so then you can work on that. Monday's lecture then will be more practice questions related to moles, grams, and the stuff we go through today on molecular shapes. And then I will post a video just so that you can rewind it and go back and forth with it. I will work out all the detailed solutions to the questions in the practice midterm. And so that will be in lieu of next Wednesday's lecture. So to kind of just recap, we'll have live lecture next Monday, but then no live lecture next Wednesday. Okay, and it'll just be a video you can watch. Okay, so I haven't even thought of how many questions yet. I'll give you, like a full 2 hours for it. It will be using Lockdown Browser, and so here's some advice. So yesterday for my large class, I have about 110 students in Chem 131. It's for, majors and, pre-whatevers. And I told them a whole week before the exam to download the Lockdown Browser. And, I gave the link on the announcements, so you can go to Blackboard, get that link. Download it, make sure your computer works, do all that ahead of the exam. And so, of course, I give 24 hours for students to take the exam. And so half the class logged in about 10 o'clock at night until, some people logged in, like half an hour before 11:59 to take this thing, so they didn't have enough time. And I was getting barraged by emails yesterday that I don't have a computer, I'm in Detroit and don't have a computer, or, it's not downloading or whatever, so the day of the exam. So I'm venting, you're future teachers, right? And so I feel I can vent to you guys. So please download Lockdown Browser like today, okay? Do it as soon as you can if you don't have it already. And make sure it works on your computer far ahead of this April 8th exam date, okay? So please, save me the stress of drinking glasses of wine to wind down yesterday over the stress of it all. Hannah, I don't know if Hannah's on the call today, but she gave some very, very good advice about taking the exam. So, you have to do it through the Lockdown Browser. You can't open it in any other, like Safari or whatever, Chrome. You have to do it under Lockdown. And make sure that it's well lit, because that was the one thing, technical issues, that I was getting some problems yesterday, although they were still able to finish it. But it would flag them if it would kind of lose their face. The settings that I have on it, if you are knocked off the internet, then it's not going to kick you out of the exam. you're still allowed then to continue where you left off. So that's a setting that I made sure I clicked on, just in case you are kicked off internet. But Hannah, wisely suggested using Ethernet cord, so get on a local area network for it instead of Wi-Fi, for instance. Although I really didn't have any problems with students yesterday with that, at least. But yeah, you make sure you have a computer that has a webcam and mic, and if you look down, so you will be able to use a calculator or periodic table of your own. I will have the first question of the exam. We'll have 2 links for you, and if you click on those links, then separate tabs will open. One tab will be the scientific calculator. The other tab will be a periodic table with all the names on it. But you can use the one that you used in previous exams if you want. Okay, and so I also made sure with the setting that if you look down, so you can use scrap paper too, by the way. And so if you look down, it's students said yesterday it didn't flag them, or maybe it flagged, but it still allowed them to do the exam. So there were no problems with them looking down, writing, and then doing the exam. Okay, so I guess any questions about like lockdown browser or anything like that? Okay, sounds good. Okay, good. Yeah, thanks again, Hannah, for those. What if my webcam doesn't work? Yeah, so it will not even let you open the exam if your webcam doesn't work. So I'm not going to have it where you have to, move the camera around a room like that, but it does a webcam check. And if it doesn't pass the check, then it won't even let you open the exam. So, at this point, you've got some time before April 8th. So, if you want to stay, safe at home, maybe get a cheap webcam off of Amazon, have it delivered to you, or, you can risk going maybe late at night to, or I guess Walmart closes early, but go to Walmart, etc., one of those stores that are still open, and get a cheap webcam. Keep your distance from people, but yeah, you do need a webcam for it. Okay. Any other questions at this time? Okay. I'll send an email with explicit, description of what coverage it will have. I can't remember even what the cutoff for the last midterm, that was before spring break, what that was. So I'll remind you kind of what sections or what chapters it will cover. So April 8th is 2 weeks. Yeah, so the midterm will be on the 8th. Yeah, and so on the 1st, I will just have instead of a live video, I'll just have a recorded video that I'll work out all of the practice midterm homework questions. So there won't be a live lecture, but it'll just be kind of a recorded video. Yeah. Okay. All right, so that's kind of the technical stuff. So let me close this so it doesn't crash. All right. So this is what we were talking about last day. So we were talking about moles, grams, and converting between everything. Okay, so this is, you multiply by Avogadro's to get number of, let's say, molecules. You would multiply by molar mass to get grams from moles, and then you would divide if you want to go from grams to moles, and you would divide if you want to go from number of something to the moles. Okay, and so here is a question, and I think we have it this way in the textbook as well. And I'm going to show you kind of the safe, longer way to do this question, but this is a simple way to do the calculation. And so this is where you want to know how much carbon dioxide is produced from burning so much of coal. And in this question, you are assuming that coal is just carbon, okay? And so, in other words, the reaction is as simple as it gets, okay? So that, okay? And so balancing is already done for you, and what's important is that you have, for every one carbon, you're generating one molecule of carbon dioxide, okay? So this little simplistic way to do the calculation will only work if you have a 1-to-1, okay? And so the way that we're doing this calculation is that you're just really using the molar mass ratio. And so carbon dioxide to carbon, if you look in the periodic table, 12.01 is carbon, and then you've got 2 oxygens that are each, remember that's 15.9994, we can just say 16, okay? And so that rounds out to 44 grams per mole. So that's the molar mass of carbon dioxide. And then just carbon is 12.01, okay? And so if you use that ratio, you can say that, if it's so many grams per mole, then the gigaton ratio will also be 44-12. Okay, and then it's just a really simple, these units cancel the gigatons of carbon. And so it's just that ratio difference between 44-12, and you get 12 gigatons of CO2. Okay, and so this, I don't actually advise you to do it that simplistically. So let me show you the way that you really should do all of these conversions, okay? And so for this one, if we have 3.3 gigatons of carbon, and you want to know how many gigatons of CO2, what you should do is, remember in this previous slide, we only really know how to calculate, grams and moles to go in between those, not gigatons. And so the first thing you should do is really convert this gigatons into grams, okay? And so on an exam, I would give you that conversion, okay? And it turns out that 3.3 gigatons, the conversion between grams and gigatons is 1 gigaton. It's actually ton, right? So this is another word. Whoop. Okay, like the metric ton, okay? So one of those is actually 1 times 10 to the 15th grams, okay? And so again, I will give you that conversion. And so that means that you have 3.3 times 10 to the 15 grams of carbon, okay? And so this is the important part, that if you want to, if you know grams of a reactant in this case, you can't convert it directly to grams of product. You have to first convert it to moles, okay? So 3.3 times 10 to the 15 grams, let me rewrite it here. How do you convert grams to moles? So what do you have to use? So if you're going from grams to moles, whoop, how come it's not working? There we go. Okay, grams to moles, we are using the molar mass. Okay, and we're dividing, we should divide by it. Okay, so let's divide by 12.01 grams per mole. Okay. So that will give you, let me do that here. So 3.3 e to the 15 divided by 12.01. And so that gives you 2.7 times 10 to the, what is that? 1, 2, 3, 14 moles. Okay? And so, so that's how many moles of carbon you have. And so now you can look at the numbers in front of the molecules or elements, And that's what's going to govern how you convert moles of something into moles of something else. Okay, and so for this one, it's a 1-to-1. And so that means that you have the same number of moles of CO2. Okay, so this is only because it's a 1-to-1. Okay, and so today, right after this, I'm going to show you examples where it's not 1-to-1, and then, it's a little more complex. Okay, so you have the same number of moles of carbon that you do CO2, and then once you have moles of CO2, how do I get grams from that? So we went from here to here. Now we're here, and we want to go back to grams. We're going to multiply, but in this case, we're using the molar mass of CO2. Okay, so that's times 44 grams per mole. Okay, and that equals times 44, 1.2 times 10 to the 16th grams of CO2. Okay, and so that's how many grams of CO2. Then to convert back to gigatons, it would just be that 1 times 10 to the 15 grams per gigaton, if we do it like that. Okay, so then we get 1.2 times 10 to the 16th divided by 1e to the 15th, and that is your 12.1 gigatons. Okay, so I think you will agree that that's a whole lot more work than this, okay? But this will not work just doing, simple ratio between the two substances won't work if, for instance, you have this. So let's do this one. Okay, and then 2 and 2, right? Okay, so now let's say we have, 2.5 grams of oxygen, and you want to know how many grams of water are produced. Okay, so now it's not as simple as just taking, let's say, the molar ratio of that to that, okay, because it's now a 1-to-2 ratio, okay? And so I guess my suggestion for you is, even though this was a lot more work, to always think of it in this term, where you're, this is more confusing, I guess, because you had gigatons and not grams directly. But, to first go grams to moles and then do the conversion, moles is something else, and then back to grams. Okay, whoops, it's not scrolling. There we go. Okay, so let me show you. Okay. There we go. So let me show you how to do this question. Okay, so now we've got 2.5 grams of oxygen. I want to know how many grams of water are produced in this. So how do I get moles of oxygen? Because remember, I can't go just grams to grams directly, right? I have to first go to so many moles, and then I can convert into moles of water. Okay, so how do I go 2.5 grams to moles of O2? Any ideas? So if I go back to this one, Okay, so I'm starting here, and so I'm going to have to use the molar mass to get to moles. Okay, so in this case, it would be 2.5 grams divided by 32 grams per mole, right? So each oxygen is 16. Okay, but you have two of them, right? Okay, so 2.5 divided by 32 is 0.078. Okay, whoops, I guess I could put it there. Okay, so that's how many moles of oxygen I have. Okay, so now here's the question. How do I calculate moles of water? And there's crickets. Okay, so just to remind you up here, right, remember we had calculated, actually let me do it like this. There we go. We had calculated the moles of carbon, and then since it was a 1-to-1 ratio, okay, just, the numbers in front after you balance, then that meant that there were the same number, right? It was just that same number of moles of CO2. Okay, so with that logic, here we've got moles of oxygen, and we want to know moles of water. So what do you think we have to do to the 0.078 in this case? And there's just a 1 in front of the oxygen and a 2 here. Double it. Yep, exactly. Yep. So here it is, let me go back to black here. Here it is a 1-to-2 oxygen to water. Okay, so that means I have to multiply it by 2, right? Because you've got 2 waters for every 1 oxygen. Okay, so 0.078 times 2 is 0.16 moles of water. Okay, so did anybody not see that? Okay, so again, you're just looking at the numbers in front of all the substances. And once you have moles of something, you could instantly get moles of something else, just either doubling it or dividing by something, or keeping it the same if it's a 1-to-1. Okay. Okay, so now we've got moles of water. We want to know grams, though. So what do I do? Yep, you multiply by the molar mass of water. Okay, so it's very typical in these questions that you start here, you go there, and then you go back to here. Okay, but you're using different molar masses in each case, right? So in this one, we use the molar mass of oxygen to get this one, and then we got here. Now we're using the molar mass of water, okay, because that's what we're interested in here. Okay, so water is 18 grams per mole. Okay, so it's 0.16 times 18, and that gives you 2.8 grams of water. Okay, so we started with 2.5 grams of oxygen, and we got 2.8 grams of water. Okay, so questions about any of those steps so far? Okay. Um, Here's a question for you for this, for this balanced equation. So let me rewrite it here because it's really messy up there. Two of those. Okay, so let's say, we have three. Okay, let's say, one question, where did I get the 18 grams per mole from? Yeah, that was just from the periodic table. So H2O, we've got 1.01, and you've got two of them, and then that was 16. So you just add them up. Okay, so does that make sense? Okay. All right, so for this, a different kind of question. If we have 3 moles of hydrogen in this case, how many moles of water are we going to produce? Three moles, yep, exactly. Yeah, very good. Yeah, and again, this is because in this case it's a 2 to 2, which, really it's the same thing as saying it's a 1 to 1, right? That ratio is the same. Okay. All right, so does everybody get that? So in a mole to mole, that's the only thing you can compare. You want to do, apples apples comparison. It has to be between moles, not between grams. Okay. And so likewise, if we had, let's say, 3 moles of this, then how many moles of water? So we kind of forget about the hydrogen right now. Okay. There we go. Yeah, so if we have 3 moles, then, yeah, it's a 1 to 2 in this case. So we'd have to multiply by 2, so that's 6. Yeah, exactly. Okay. All right, so here is a calculation I want you to take a stab at then. So let's look at these two examples. So let's say methane. Okay. Versus, let's look at octane. So what's the formula for octane? C8H. Do you remember from previous? So you double and then, yep, 18. Yep, exactly. Okay, goes to CO2 and water. Okay, so what I want you to do is calculate how much CO2 is produced from, let's just do 1 gram of methane and 1 gram of octane. This is a component of gasoline, okay, versus this is natural gas. Oops. Okay, methane is natural gas. And so with 1 gram of each of those, I want you to calculate how many grams of CO2 is produced. And here's a hint for you. Your first step in any of these questions is to balance it first. Okay, so these numbers are really important, right? So if you don't have these right to begin with, there's no way you'll get the right answer. Okay, so I want you to take a few minutes and balance each of these reactions. Okay, and then calculate how many grams of CO2 is produced from 1 gram of methane versus 1 gram of octane. Okay, so I'm going to just pause the recording while you're working on it, and ask questions as you're working on it too, if you're stumped by any of these steps. Okay. Balancing. Who can tell me what the first equation, what you had for the coefficients? So methane, oxygen, CO2, and water. Yeah, so 1, 2, 1, 2. Okay, yeah. So yeah, I would do carbons first, they're balanced. Then maybe hydrogen next. So you put the 2 in front. And then you leave oxygen till last. Yep, and so that's good. Yeah. Okay. And then how about the second reaction? Okay. Yeah. So just waiting for the second. Okay. Right. So I will shut up and let you work here then. Okay. So did anybody balance at least the second reaction so far? Just to get those out of the way first. So it's one of those that you have an odd number on, I see. Yeah. So 2, 25, 16, and 18. Okay, so let's see. So that's 16, 50 oxygens. 32, yeah. Yeah, so that is correct. Yeah. Okay, so are you still working then on the grams part? Or did anybody do that for the methane one? Okay, so to kind of go through this. So if you have 1 gram, I guess I should be a little more explicit here. Okay, so if we have 1 gram of methane, then how do I get its moles? Yeah, so you divide by its molar mass. Yeah, so carbon is 12, hydrogen, each of those are 1. So what is that, 16 grams per mole? Okay, so what is that? So 1, divided by 16. So I get 0.0625 moles of methane. So how many moles of CO2? Yep, exactly. It is the same. Yeah, because you have a 1 in front of methane. How come it's not showing? There it is. And a 1 in front of CO2. Okay, so it's 0.0625. And so now if you want to get grams, then you would multiply by this molar mass. So that's 44 grams per mole. Times 44 is 2.75 grams of CO2. Okay. So any questions about methane then? So 1 gram of methane gives 2.75 grams of CO2. Okay. All right, so now let's do the bottom one. Okay, and so in that case, this is actually a really important point too. Okay, so to get moles of octane, you're going to divide by the molar mass. Here's the thing to really keep track of. When you're divided by molar mass, do not use the 2 in front of it. It is just this. Okay, so it's just C8H18, which, what is that? 12 times 8, and we've got another 18. So that's 114 grams per mole. Okay, so never, like for this one, if you had a 2 in front of the CO2, you wouldn't multiply by like 88 or something like that. Okay, it's only the molar mass of the compound. In other words, these numbers in front, once you've converted moles of something to moles of something else, then forget about these numbers. Don't use them again. Okay? All right, so you do 1 divided by 114. And so that gives you, in this case, 0.0088 moles of octane. Okay, so the million-dollar question, how many moles of CO2? So this now is where you're using these numbers in front. Okay. Yeah, you multiply by 8, correct. Okay, so for this one, you have a 2 to 16 ratio, in other words. Okay, so you have to multiply by 8. So times 8 gives you 0.070, I guess, moles of CO2. And then times the same molar mass as before. So we get 3.1 grams. Okay. So is everybody cool so far? Any questions about that difference? Okay. All right, so kind of who cares, right? What I want to point out is why it matters what type of hydrocarbon you use in your vehicle or at home. Okay, so this methane is what we use in our homes to stay warm. Octane, that's gasoline, so we use that in our vehicles. And so hopefully you can see with this, it's not a big difference really, but for every gram of your fuel, you are getting more CO2 for gasoline than you are methane. Okay, and so that's why you see in some cities, I would see this in China a fair amount, but even San Francisco, some of these other cities, of course pre-lockdown, but you see natural buses. They're city buses that are run on natural gas, and so you're saving on a greenhouse gas that we're going to get into here shortly. So CO2 is one of the gases that is responsible for the greenhouse effect or global warming. Now we call it climate change. And so you're getting more CO2 if you burn gasoline than you do burning methane. Okay. And what we're going to see actually is that CO2 is not the only greenhouse gas, but water is as well. And so if you just look at these numbers, you can see, it's kind of like a 1-to-2 ratio for going, moles of methane to moles of water. Here it's going to be a 2-to-18, or like a factor of 9. Okay, and so for every gram of octane, you're getting more CO2 and more water as well. Okay, so you're really spitting out more greenhouse gases from burning gas than you do natural gas. Okay, so does that kind of make sense? Okay, hopefully so. How do I get past the screen? There we go. Okay. All right. So getting back to now, we're hopefully getting comfortable going between grams and moles. Okay. Now the other conversion is going between moles and number of something. Okay. And so a couple questions ago we calculated that 3 gigatons of carbon resulted in 12 gigatons of CO2. Okay, so we want to know now how many molecules of CO2 that corresponds to. Okay, and so now what we're doing is we're going to use this conversion. Okay, now we're going to have to go to from gigatons to moles. And then once we're at moles, we're going to use Avogadro's number to get individual molecules. Okay, so it's going to be that really, really large number. Okay, and so here's the strategy. So again, you're using the molar mass for CO2 is 44. And so here we have to convert gigatons to grams. Okay, and that's that conversion factor again. So 12 is 1.2 times 10 to the 16th grams of CO2. And then once we have that grams, we divide by its molar mass. Okay, so that gives you a huge number of moles of CO2. Okay, and then once we're at moles, that's where you then multiply by Avogadro's number. Okay, and then you get this insanely large number of molecules. Okay, so 1.6 times 10 to the 38th molecules. Okay, so large that it really is kind of meaningless to us. Okay. Okay, so is everybody cool with that? Okay, so to go from a mass in some unit to number of something, that's when we're using Avogadro's. Okay. So for this question, we calculated, let's say for, octane, that was 3.1 grams of CO2 molecules. Okay. How many molecules does that correspond to? Okay. So for this, it's a much smaller number, right? So we have grams, so we divide by the molar mass. Okay, so that gets, so what is that? So 3.1 divided by 44 is 0.070 moles of CO2. Okay, and then we just multiply by Avogadro's number. Okay, again, I would give you that on the exam too, okay, in case you forget. 6.02 e to the 23rd gives you, in this case, 4.2 times 10 to the 22 molecules of CO2. Okay? So hopefully everybody is getting these little conversions, back and forth, okay? I'll have, a few of these, of course, on your next midterm. So your practice midterm will have a few of these, and then we'll go through maybe a few others on Monday of next week just for practice. Okay. All right, so before getting back into the context here, any questions at all? Hopefully you haven't, I haven't put you into a nap here, afternoon nap. Okay, I'm not seeing any, so, okay. So we're talking CO2 here, okay? And so this is kind of a really, really complicated figure, and it's something that really doesn't make sense. The numbers don't make sense just looking at it, so I have to walk you through this. This is showing what, we used to call, we still call it the greenhouse effect. It's just that, the warming that we've experienced, it's causing a lot of other kinds of climate effects, like, increased hurricane number and intensities, etc. And so that's why it's, kind of a broader umbrella. The climate research community figured, let's just call it climate change, okay? But you still could call it greenhouse effect. And so this is what happens when the sun is hitting the earth, okay? And so this is, we start with 100, so 100% of intensity from the sun. Some of it is absorbed in the atmosphere, so it doesn't, reach Earth. And so really only 46% of the sun's radiation reaches Earth, okay? And so the other 54% is absorbed or reflected, okay? And that's all of these numbers. Okay, so this is absorbed. And so if you add up this, this, and this, so these blue ones, and this other yellow, you will get 54%. Okay, so 23, 25, and 6, okay? And so of this 46%, 37% of it is re-emitted in the form of infrared radiation, okay, or heat, in other words. Okay, and then the other 9% is just emitted into space, okay, emitted from the surface. And so if you look at the numbers here, so 37% divided by 46, that's about 80%, okay, of radiation that is absorbed by Earth is trapped by our atmosphere. Okay, so I'm just doing 37 divided, so this divided by that, okay? And so it's a good thing that that happens, actually. And so this is the one take home that I want you to appreciate here. If we treat this class kind of like a citizens first class, where you someday are going to be in front of students and parents and everything, and I don't want you to you know propagate all these kind of myths in the media or hype. So the greenhouse effect does not have to be a negative thing. It's actually a great thing that it happens. And so it's a wonderful thing that we've got 80% of this radiation that is trapped, because that gives our planet an average temperature of about 15 degrees Celsius. Okay, that's global average. Okay, of course, some places are warmer, some places are colder. But if you didn't have this happening, okay, so let's say it was absorbed, and then all 46% was this. It was just emitted out. And so in other words, it would kind of just bounce here and go back out. Then our average temperature on Earth would be minus 18 Celsius. Okay, and oceans would be frozen year-round. There would be many places of the planet uninhabitable. Okay, and so the greenhouse effect is a good thing if you can just keep this to kind of 80%. Okay, but what happens if more heat is trapped by the atmosphere? Okay, and so a case study in this is actually Venus. Okay, so the planet Venus has a lot more CO2 concentration. Okay, so by the way, these brackets mean concentration. Okay, and so that has much greater CO2 concentration than Earth. Okay, and as a result, its average temperature is much, much higher. Okay, so it's actually so high that life couldn't be present in Venus. Okay, and so that is due to CO2. Okay, and so if you have this atmosphere that has a greater concentration of CO2, then it's going to trap more and more of this radiation. Okay, so instead of 9% being emitted, maybe only 6% at a certain point. Okay, and so you're just trapping more heat in this atmosphere, and so it's going to warm our planet more. Okay, and so I don't really get the argument, I will grant you that there could be natural cycles involved. Okay, so the Earth is heating. Okay, so in recent years, the average global temperature is going up. And, there are some data that show that there's sunspots that are more intense, in recent years, etc. So there could be some natural causes for that. But, from the Venus case study, we know that if there's more CO2 in the atmosphere, more sun is trapped, and so the temperature goes up. And so, just from, thinking of just a greenhouse, right? If you have a greenhouse, you're trapping in more heat. It can't escape as much. And so I don't see why people have such a hard time, rationalizing how it's possible that humans can cause this, okay? And so how is radiation absorbed? Okay, and so we talk, that 80% is absorbed by atmospheric gases, but only certain gases will absorb infrared radiation. Okay, and so it turns out that CO2 and water will absorb IR radiation, but most of our atmosphere is actually nitrogen and oxygen, right? So you've got 78% nitrogen, like 21% oxygen, and then these are just parts per million type. Okay, and so the majority of the gases in the atmosphere don't absorb this infrared. Okay, and so we're going to talk today, this last part, about what features a molecule has to have for it to absorb infrared radiation. Okay, and the first thing I want to talk about is that Remember, UV light is able to break bonds. And we're talking here covalent bonds. Okay, and remember, for instance, UV light would break that into that. Okay? If we have IR light, it's not intense enough to break bonds, but it can cause stretching or bending of covalent bonds. Okay, and so that is what happens when you have CO2. Okay, and so remember, we're going to have to get back into Lewis structures here. So nice review of that. But that's the Lewis structure of CO2. And so when infrared radiation hits this molecule, all that happens is that these bonds stretch. Okay, so they go back and forth. They can either do it, where this bond stretches at the same time that one does, or maybe they're off sequence. Okay, but they're just stretching. Okay, and so molecular vibrations, all these vibrations are related to the shape of the molecule. Okay, and so for us to predict shapes, we have to start with Lewis structures, and then there'll be some rules that we're going to follow to figure out, to go from the Lewis structure to shape. And the theory that governs this is kind of a mouthful. It's valence, shell, electron, pair, repulsion, or Vsepr theory. Okay, so something to impress somebody at a bar or whatever, with this. And what it really means is that electrons occur as pairs, really, in bonds, and as lone pairs. And they mutually repel one another. Okay, so electrons are negatively charged, right? And so they want to get out of each other's way. Okay, and so if we have this Lewis structure, okay, so this is CO2, and actually let me go through the steps for this again, just to remind you guys. Okay, so CO2, the Lewis structure for CO2, what do we need to know to draw its Lewis structure? Do you remember? This is going back now a little while. So we had to add up something.
The total valence electrons?
Yes, exactly. So we had to add up all the valence electrons, and so oxygen each had 6. Okay, and you have 2 oxygens, and then carbon had 4. Okay, so that's 16 valence electrons. Okay, and then we put carbon in the middle. Okay, and then we draw our single lines. So I've placed 2 and 4 there. Okay, whoops, let me. Okay, so I place 4, and then I start building up around the outside. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and then remember we would have to look and see, do you have an element here that absolutely needs an octet or 8 electrons around it, but it doesn't have it? And so is there one here? So the oxygens are happy, right? Because they're surrounded by 1, 2, 3, 4, 5, 6, 7, 8. Okay, because there's 2 in that line there. And then same with this one. Okay. But the carbon has to have an octet. Okay. And so it only has 4 right now. So the way we do that is we say, let's move these 2 over to there. And then let's move maybe these 2 over to here. Okay, so in other words, without my scribblies here, that is the Lewis structure for CO2. Okay. All right, so yeah, so oxygen had an octet. It was carbon that was the one that didn't. Okay, and now everything is happy, right? Because you've got 1, 2, 3, 4, 5, 6, 7, 8 around carbon, and you've got 8 around the oxygens. Okay, so here's how. And in previous semesters, I would really kind of take off on this because I really like this topic, I guess. And I think, I mean, this really is important for a lot of different contexts. I'll spare you a lot of the geometries or shapes this semester. We're just going to go through a few simple ones. So you can thank me later. And so here are some rules. So how to predict shapes. Okay, and I'm going to designate these molecules by AX something, okay, where this is your central atom, and then these are all your peripheral. Oops, if I could spell. Okay, and so for instance, CO2, I would call that AX2. Okay, and then if there are any lone pairs around it, around the central atom, okay, so if lone pairs around the central atom only, then I'll call it like AX and LM or something like that for the number of lone pairs. Okay, so for instance, if we have water, okay, remember the Lewis structure for water was this. Okay, so water, I would designate it as AX2L2, okay, because I've got a central atom. Oops, I've got a central atom. I've got 2 things around it. And then I've got 2 lone pairs, 1 and 2. Okay, so does everybody kind of get, you know, what I mean by AX whatevers, or AX with L's? You know, just indicating like how many lone pairs are on the central atom, and then how many things or how many different atoms there are around the central atom. Okay. Okay, so here is the little table then. So we'll do molecule and shape. Okay, and so the first one we looked at was AX2. Okay, and an example of that, I'll just put in parentheses here, is CO2. Okay, so in other words, no lone pairs around the central atom. Okay, and if we look back at CO2, we see that, right? There's nothing around it here, no lone pairs. Okay, so the shape of this is just called linear. Okay, so CO2, in other words, would look like this, where this angle is 180 degrees. Okay. All right. The next one is, let's do this. Okay, AX2L. Okay. And so, maybe that's, I said I wasn't going to get carried away, so let's see. Okay, yeah. Let's just go to AX3. Okay. Okay. So this would be a central atom with 3 atoms around it. And so it is going to be one of the exceptions to the octet rule, right? Because you only have 3 instead of 4 things around it. And so this, remember, was something in like group 13. Okay. So remember, if I go, where's a little space here? Okay, so remember BCl3 looked like this, the Lewis structure. Okay, and it was totally happy. So boron was happy having only 6 electrons instead of 8 because it's an exception to the octet rule. Okay, so group 13 is one of those exceptions. Okay, so that would be AX3. No, so again, no lone pairs around the central atom. And so that would be, so if we're going to use kind of one example here, that would be called trigonal planar. Okay, meaning that these angles are all, no, it's not, 120. Okay, so all those are 120. And it's on the plane of this paper, okay, of my iPad. Okay, so trigonal planar is that geometry, or that shape, okay? All right. The next one is if I add a lone pair to that. Okay. And so let's look at the Lewis structure for what we call ammonia. Okay, a lot of cleaning products have ammonia in it, it's NH3. And so if we look at ammonia, you have how many total valence electrons in ammonia? So nitrogen is in group 15 or 5A. Okay, so that's 5 valence electrons for nitrogen and then 1 for each of the hydrogens. So that's only 8, right? So 8 valence electrons. And so we can draw it like this. Okay, remember hydrogen is also one of the exceptions. It's totally happy with 2 valence electrons around it. It doesn't have to have 8. And so that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so this geometry has, you'll notice, so this is where I get the AX3L is this lone pair. Okay, and now instead of it being trigonal planar, it's going to be trigonal pyramidal. Okay, and I think I have a picture of what that looks like here. Yeah, like that. Okay, so the angles are now, instead of it being 120, they're a little bit less. Okay, so it's now 107 degrees. I'm not going to have you memorize these values. You should know, this one, for instance, 120, and then that one 180, if it's linear. But these ones, it's fine if you say that they're less than 120. Okay, and the reason why these angles are a little less is because a lone pair, these are 2 electrons, and then you have, remember, 2 electrons in here, and they're going to repel each other. Okay, and so this takes up more space, a lone pair does, And so you're going to repel these bonding electrons to a greater degree, and so the angle goes from 120 to less than that. Okay, in this case, 107 degrees, so pretty significant drop in this angle. Okay. And so again, this whole theory, it's a simple theory that is all related to electron pair repulsions. Okay, so just repelling, electrons repelling one another. Okay. Okay, so is everybody cool so far? So we've looked at linear, trigonal planar, trigonal pyramidal. Okay, and then AX2L2. Okay, and this is our friend water. Okay, so if we were to do the Lewis structure for water, it's this. Okay, and so that's your AX2, and now we've got L2. Okay. And so because of this, you're getting a lot of repelling, okay, between the lone pair and the bonding electron. So this is 104.5 degrees. Okay, so it's even less. Okay. And so this is just known as bent. Okay. All right. And so there's only one more that I'm going to talk about in this class, and so that is AX4. And this is, for instance, methane. Okay. And so in this case, methane. This one is kind of hard to draw. So I'm trying to show is that I've got two hydrogens that are in the plane of the paper, one that's coming out and one that's going back behind the page. Okay, and all these angles are 109.5 degrees. And so this is called tetrahedral as the shape. Okay, and that one looks like this. Okay, so all the angles 109.5. Okay, and it's kind of like a good analogy of it is a music stand. Okay, so this is what it kind of looks like. Okay, if you imagine that carbon is in the middle, and then at the end of each of these is where the hydrogens are. Okay, that is a good analogy for the tetrahedral shape. Okay, and then if you want to know, this ammonia shape, where we talk trigonal pyramidal, it's like this, and then you remove this top one. Okay, so it's just this tripod. So this is nitrogen, and then those are your three hydrogens there on the tripod, and then you've got a lone pair here. So that would be your trigonal pyramidal shape. Okay. And so those are the only shapes we are going to talk about in this class. Before, I think I would go through, I don't know, like 12 or 15 different shapes. So that was really TMI, I think. And so these are the most common ones that you're going to see. Okay, so you're going to see linear bent shapes like water, okay, trigonal planar, trigonal pyramidal, and tetrahedral. Okay, and so looking back then at kind of these different shapes, this is kind of a comparison of three molecules we've talked a lot about so far. So there's CO2, there's water, and there's ozone. Okay, so ozone, remember, has this Lewis structure, so it's a resonance form. So you've got this, and then the form where the double bond is here instead. Okay, but since you have a lone pair on the central atom, it has to be bent as well. Okay, and so that one, I guess, by my designation for ozone, it would be, I guess, like AX2L or something like that. Okay, where you just have one lone pair around the central, like that. And then this, for instance, okay, for each of the resonance forms, okay? But what's really important here, what governs shape is lone pairs on the central atom govern the shape. Okay, notice for any of these geometries that we talked about, I could care less how many lone pairs are around here, okay, on the outside. I am honing in on this lone pair, okay, because that is the one that's going to repel these bonding electrons, okay. And so, for instance, for CO2, it didn't have any lone pairs around the central atom, and so that's why it is linear, okay, because there's nothing to repel these bonding electrons. Versus water, if I draw it like this first, okay. Now, do you notice the difference? That now you've got these lone pairs that will repel those bonding electrons, and that forces it to be bent. Okay? And so this is so critical to life, really, that it's this serious. You know, we're going to talk, kind of one of the last topics we're going to talk about this semester is intermolecular forces, and that is, you know, how do two hydrogen or water molecules interact with one another, for instance. So that's called an intermolecular bond, okay? And so we're going to talk, you know, more about this later, but it's so critical. The shape of molecules is so critical that if water were linear, so if this would be the shape for water molecules, then we would all be dead. Okay, so electrolytes, salts would not dissolve in our blood system that's mainly water. You know, our bodies are mainly water-based. And so we wouldn't be able to have protein structures like we have, etc. Water would not freeze at the temperature it does, and so you wouldn't be able to have aquatic life. And so just life on Earth is possible because of this shape. Okay, so it's that fundamental for everything. Okay, and the reason it has the shape is because of these lone pairs. Okay, and so you can really say, you know, lone pairs influence life on Earth. Really, they're that important. Okay. All right. So I think that is a lot for you to digest again. And so what we're going to talk about after the midterm is, now we've talked about molecular shapes, and we've got, you know, these, I guess probably the summary slide is better. Yeah. So you've got these 5 different shapes, and we're going to talk about how do these different molecules absorb infrared radiation. Okay. And so we know nitrogen, oxygen do not. And so we're going to look at what's different between N2 and O2 versus these two, for instance, that will, you know, be very effective to absorb IR versus N2 and O2 don't. And so we're going to really look back at that context and kind of pull this together in kind of one final summary lecture on Chapter 4. Okay? All right, so any questions before we sign off? I am not hearing any. Okay, so I wish you a good weekend, a good rest of the week, And I will see you all on Monday. And I will email you as soon as I post the practice midterm homework assignment. Okay. All right. Take care, everybody.